I was born under a wandering star, a wandering star.
And because the Greeks thought the Earth was at the center, they had to come up with other theories to explain why the planets would move forward and backward while still traveling in perfect circles. Greek astronomers thought they knew the answer. The planets must move in what they called epicycles.
And this is really just, in a sense, a circle on a circle, or a sphere on a sphere. If you imagine that a sphere is turning and there's an object on it turning that way, but it's also attached to another smaller sphere that's going in the opposite direction, that means that now and then it goes backwards.
It's like a teacup ride at an amusement park. Small circular orbits on top of a large spinning platter. Sometimes it appears as though the teacups are moving backwards. The Greeks thought the 5 visible planets must move in similar patterns. 110 years ago, Greek sponge divers anchor near a small barren island in the Aegean Sea, Antikythera. One man puts on his diving helmet and drops down. He soon surfaces, horror-stricken and ranting.
Apparently terrified, gabbling about a pile of dead, naked women that he'd seen on the seabed. So the captain went down to have a look for himself and realized that these were not naked women, but statues, bronze and marble statues from the ancient world. It turned out that this was an ancient wreck that held one of the most important hoards of ancient treasure that had ever been discovered up until that point.
The priceless artifacts are proudly displayed at the National Archaeological Museum of Athens in Greece. But hidden among them is something odd.
It looked like just a piece of battered rock, but inside there were gear wheels, pointers, inscriptions. This looked like some sort of clockwork machine, which just shouldn't have existed in the ancient world, according to historians of the time.
These were the earliest such gears ever found, by over 1,000 years. The ancient Greek device is now known as the Antikythera mechanism, after the island where it was found.
It might be really interesting.
What was important for them was gaining knowledge, gaining an understanding of the cosmos, using technology to elevate the spirit by getting closer to the gods, closer to the nature of things.
Their pantheon of gods ruled over a perfectly ordered universe, and the gears in this ancient computer were a mechanical celebration of it, a way to understand the planets, stars, and moon as they swirled above. Within a few hundred years, though, ancient Greek civilization would die out, and the knowledge that made this computer would die out with it. Thousands of years ago, Babylonian priest astronomers carefully recorded what they saw in the night sky. Centuries later, those records passed to Greek astronomers, who used that knowledge to create geometric models of the solar system and predict future alignments of the planets and stars. Over the course of a single month, the moon gradually speeds up and slows down in its path across the sky. The geometrical formula to describe the moon's variable speed was worked out by a man named Hipparchus, the founder of trigonometry. He worked in the 2nd century BC, 100 years after Archimedes.
Without Hipparchus, or somebody like him, the thing could not have existed. Hipparchus played the key role in taking the translated Babylonian data, transforming it into a set of models that actually worked to actually predict the positions of the sun and the moon.
This is a reconstruction of a 2,000-year-old computer. The original battered pieces were found in a shipwreck more than a century ago, and Michael Wright A museum curator from London spent decades studying them in order to work out what the device was for. He built this model in his home workshop with techniques similar to those that the Greeks might have used.
This is my model of the Antikythera mechanism. The mechanism is a box full of gear wheels driving indications on dials, one at the front and one at the back, which we'll look at in a moment. And it's all driven by working from the hand knob here. On the front dial, we've got two scales. The inner ring is the zodiac divided into degrees. The outer ring is an annual calendar scale, 365 days.
The device is a machine for predicting the motions of the heavens. When you turn the handle on the side, pointers move around the front dial, showing the movements of the sun, moon and the 5 planets that the Greeks knew. The fastest pointer here is for the moon, going around the sky once a month, while the white and black ball shows its changing phase. Inside, a sophisticated setup of wheels riding around on other wheels models the varying motions of the planets, according to the Greeks' astronomical theories. As the side handle turns, the planet pointers sometimes move forwards and sometimes backwards. Meanwhile, the sun and moon pointers vary in speed, just as the actual sun and moon do when seen from Earth.
Now we'll look at the back. We've got two sets of two displays together here. The upper one is basically a calendar. The spiral scale is divided into months, each of which is named, and this is a cycle of months, 235 months, which fit into 19 years. These are months measured by the moon.
An extendable pointer with a little needle on the end tracks the spiral groove, just like the stylus on a record player. When it gets to the end, you can lift the pointer up to reset it. One of the little dials just inside the spiral shows the dates of the ancient Greek games, including the Olympics on a 4-year cycle, while the other tracks a much longer 76-year cycle.
The lower display is giving the times at which there may be eclipses. Again, it's graduated into months, and the markings are just in those months in which we expect there to be an eclipse either of the moon or of the sun or of both. The thing about eclipses is that they happen according to a pattern which repeats after 223 months. So here we have a 4-turn spiral scale with 223-month divisions.
This dial is one of the most exciting parts of the mechanism. It was used to predict eclipses of the sun and moon according to a repeating 18-year cycle. The Greeks probably got the data from ancient Babylonian astronomer priests who had been observing eclipses for centuries. Inside the mechanism, you can see the gear trains that drive the pointers on the back dial. This shot also reveals that this model was made of recycled metal plates, just like the original would have been. This is the first model of the Antikythera mechanism to incorporate all of its known features. Thanks to Michael Wright, it's working again for the first time in 2,000 years.
The Greek word for planet is planetes, meaning wanderer. It's an apt name because these objects seem to move almost randomly across the sky. The Greeks could see 5 planets with the naked eye, all traveling along the zodiac, the same narrow path that the sun travels past the stars. Like the moon, planets speed up and slow down. But sometimes, planets appear to go backwards.
The planets are a whole different trip. They're all over the map. Some of the planets are just continuing to progress, in a sense, forward through the sky, and then they seem to back up. And then they go forward again, totally off the wall as far as the astronomy seemed to be concerned.
Somehow,
Retrograde is simply a word that means backwards. It just means that an object is moving in the unaccustomed direction.
But the planets aren't actually moving backward. It just looks that way from Earth. It's like driving next to a car on the highway. There is continuous forward motion, but varying speeds give one car the appearance of moving backward.
He catches up and overtakes me. And here's where you get retrograde motion.
From the Sun's perspective, all the planets move forward continuously. But because the Earth is also moving, from our perspective, the other planets appear to slow down or even travel backwards at times.
Tycho was a wonderfully colourful character. When he was a student, he lost a large chunk of his nose in a duel and had it replaced with a metal one. Legend has it he kept a dwarf under his table, and he believed that that dwarf was clairvoyant. He also apparently kept an elk, which fell down the stairs when drunk and died. There is, however, one thing about Tycho which is absolutely certain. He was a passionate stargazer.
Science needs evidence, and Tycho was a new sort of data gatherer. He built a vast observatory and equipped it with the best instruments money could buy. And so was his commitment, night after night for over 20 years. He was putting together a unique body of evidence that would in time reveal the secrets of how the planets move.
Right, so we've got the moon over there.
Now this is how you make an observation with Tycho's quadrant. It of course is pointing at the moon. You take the sighting arm, you sight it exactly upon the moon. You would look through the upper slit across the upper part of that central brass peg.
Yep.
Then the lower slit through the lower peg. So the upper and the lower cusps of the moon, the points of the moon, were between them.
So you've got it lined up, essentially, now.
Absolutely lined up.
OK, so I get that as 16 degrees and 40 minutes of arc.
That sounds perfectly reasonable.
OK, and that is logged the moon on the 26th of May, just past 10 o'clock.
Just past 10 o'clock.
So he would go on plotting these details throughout the night, basically.
Yeah. Well, of course, not from the moon. The moon would set. We'd do it for planets, as things appropriately came in the sky, and build up these great observing logs of raw data. And out of that, of course, is what the heart of science is. Tycho starts this tradition of science not just being about information and theories, about data, information and analysis from fresh observations.
Books and books of it, presumably.
Absolutely.
Having seen you in action now, what I'd like to do now is look at a star, really the pole star, the North Star.
Pole star, which of course everything rotates around, the star over here.
What Tycho was doing represents something really important in the emergence of science. A commitment to cold, hard, obstinate facts.
I can see it now. I'm lining it up with that, and
that is 51 degrees and 36 arc minutes.
Right, excellent. So that's my first star.
It is indeed, not bad at all.
Thank you. I've got 776 to go.
Congratulations.
Thank you.
It's a shame that the craftsmen who built such beautiful instruments and men like Tycho who used them get so little credit. Because the evidence that he gathered would in time undermine a belief system that had dominated Western thought for over 2,000 years.
The planets orbit the Sun in a counterclockwise direction as viewed from above the Sun's north pole. And the planets' orbits all are aligned to what astronomers call the ecliptic plane. The story of our greater understanding of planetary motion could not be told if it were not for the work of a German mathematician named Johannes Kepler. Kepler lived in Graz, Austria, during the tumultuous early 17th century. Due to religious and political difficulties common during that era, Kepler was banished from Graz on August 2, 1600. Fortunately, an opportunity to work as an assistant for the famous astronomer Tycho Brahe presented itself, and the young Kepler moved his family from Graz, 300 miles across the Danube River, to Brahe's home in Prague. Tycho Brahe is credited with the most accurate astronomical observations of his time and was impressed with the studies of Kepler during an earlier meeting. However, Brahe mistrusted Kepler, fearing that his bright young intern might eclipse him as the premier astronomer of his day. He therefore let Kepler see only part of his voluminous planetary data. He set Kepler the task of understanding the orbit of the planet Mars, the movement of which fit problematically into the universes described by Aristotle and Ptolemy. It is believed that part of the motivation for giving the Mars problem to Kepler was Brahe's hope that its difficulty would occupy Kepler while Brahe worked to perfect his own theory of the solar system, which was based on a geocentric model where the Earth is the center of the solar system. Based on this model, the planets Mercury, Venus, Mars, Jupiter, and Saturn all orbit the Sun, which in turn orbits the Earth. As it turned out, Kepler, unlike Brahe, believed firmly in the Copernican model of the solar system known as heliocentric, which correctly placed the Sun at its center. But the reason Mars' orbit was problematic was because the Copernican system incorrectly assumed the orbits of the planets to be circular. After much struggling, Kepler was forced to an eventual realization that the orbits of the planets are not circles, but were instead the elongated or flattened circles that geometers call ellipses. And the particular difficulties Brahe had with the movement of Mars were due to the fact that its orbit was the most elliptical of the planets for which Brahe had extensive data. Thus, in a twist of irony, Brahe unwittingly gave Kepler the very part of his data that would enable Kepler to formulate the correct theory of the solar system, banishing Brahe's own theory. Since the orbits of the planets are ellipses, let us review three basic properties of ellipses. The first property of an ellipse. An ellipse is defined by 2 points, each called a focus, and together called foci. The sum of the distances to the foci from any point on the ellipse is always a constant. The second property of an ellipse. The amount of flattening of the ellipse is called the eccentricity. The flatter the ellipse, the more eccentric it is. Each ellipse has an eccentricity with a value between 0, a circle, and 1, essentially a flat line, technically called a parabola. The third property of an ellipse. The longest axis of the ellipse is called the major axis, while the shortest axis is called the minor axis. Half of the major axis is termed a semi-major axis. Knowing then that the orbits of the planets are elliptical, Johannes Kepler formulated 3 laws of planetary motion, which accurately describe the motion of comets as well. Kepler's first law. Each planet's orbit about the Sun is an ellipse. The Sun's center is always located at one focus of the orbital ellipse. The Sun is at one focus. The planet follows the ellipse in its orbit, meaning that the planet-to-Sun distance is constantly changing as the planet goes around its orbit. Kepler's second law. The imaginary line joining a planet and the Sun sweeps equal areas of space during equal time intervals as the planet orbits. Basically, that planets do not move with constant speed along their orbits, rather their speed varies, so that the line joining the centers of the Sun and a planet sweeps out equal parts of an area in equal times. The point of nearest approach of the planet to the Sun is termed perihelion. The point of greatest separation is aphelion. Hence, by Kepler's second law, a planet is moving fastest when it is at perihelion and slowest at aphelion. Kepler's third law. The squares of the orbital periods of the planets are directly proportional to the cubes of the semi-major axes of their orbits. Kepler's third law implies that the period for a planet to orbit the Sun increases rapidly with the radius of its orbit. Thus, we find that Mercury, the innermost planet, takes only 88 days to orbit the Sun. The Earth takes 365 days, while Saturn requires 10,759 days to do the same. Though Kepler hadn't known about gravitation when he came up with his three laws, they were instrumental in Isaac Newton deriving his theory of universal gravitation, which explains the unknown force behind Kepler's third law. Kepler and his theories were crucial in the better understanding of our solar system dynamics and is a springboard to newer theories that more accurately approximate our planetary orbits.
One billion stars. This is the number that the European Space Agency mission Gaia will reach, mapping each star over 70 times to nail down their position, movement, and characteristics. In the end, we will hold in our hands the most precise three-dimensional map of our galaxy. But how exactly will the mission measure such a vast number of stars? With its two telescopes, Gaia looks at two patches of the sky at the same time. A series of mirrors guides the light to the camera, the most powerful camera ever flown in space, with 106 CCDs and almost 1 billion pixels. When light from the first telescope reaches the camera, the first column of CCDs in the star mapper, on the right, selects the stars that will be followed and measured. When light from the second telescope reaches the camera, the second column of CCDs in the star mapper selects the stars that will be measured. As Gaia scans the sky, the light from both telescopes moves across the camera. But not all data need to be read out and stored. The onboard computer assigns a small patch or window around each star. As the image of the star moves across a row of CCDs in the camera, the star's position and brightness in this small patch on each CCD are recorded. This method is an optimization to deal with the enormous amount of data collected by Gaia's camera. Only a few dozen pixels on each CCD contain information about the star, so only those are read out and the corresponding data stored. The largest section on Gaia's camera is the astrometric field. As the image of a star moves across its 9 columns, each CCD measures the star's position and brightness. Then the starlight passes through two special prisms that direct different wavelengths to the 2 columns of CCDs in the photometer. This provides information about the star's temperature, size, and chemical composition. Light from a subset of stars also reaches the radial velocity spectrometer, 12 CCDs that are used to measure how fast stars are moving with respect to us. For each star, the information collected by all CCDs is compressed into a data packet and stored in the computers on board Gaia. This process is repeated over and over for each star. An average of 2 million stars are measured every hour, generating a total of about 50 gigabytes of data every day. This is equivalent to more than 10 DVDs worth of information every day. The data packets for each star are transmitted to Earth, where they are received at the European Space Agency's ground stations. The data are processed and analyzed by astronomers, who use them to investigate the three-dimensional distribution and physical characteristics of stars. When all this is done, Gaia will have created the most precise three-dimensional map of our galaxy, the Milky Way.